Hi guys, greetings to everyone. Welcome once more to another video in our YouTube channel. In today's video, we are going to be continuing the sequences and series. So this is part 2 of the sequences of the recursive sequences and series. So part 1 was basically talking about the generalities on recursive sequences and series. So for those of you who have not watched part 1, endeavor to watch part 1 after watching this video. I am going to include the video link to part 1 in the description and in the comment section so that you can find yourself there already. So like we promised in part 1 that in the subsequent parts we are going to solve the Cgce equations. So part 2 we are going to be looking at June 2021 further maths paper 2 question that came in this topic. So without wasting much of your time, let's get started. So let's get started with the question. So the question has been displayed. So that's the useful information that's been displayed. And then Roman 1 is asking us to show that Wn is a geometric progression and we should give the expression of its n term. Roman 2 is asking us to find the limit as n tends to infinity of Wn. Roman 3 is asking us to express un plus 1 minus un in terms of Wn. Roman 4 says, hence or otherwise, show that un is equal to 14 minus 20 times 5 on 6 raised to the power n. Roman 5 is asking us to study the sense of variation, that is the monotony of the sequences un and vn. Roman 6 is asking us to find the limit of un and deduce the limit of vn. And Roman 7 is asking us to evaluate the sum from n equal to 1 to infinity of un minus 14. Alright, so we are going to begin with Roman 1, which is asking us to show that the sequence Wn is a geometric progression and we should give the expression of its n term. So like in part 1, I'm just going to give the hints. We said that to show that a sequence is geometric, we just need to show that the ratio between the n plus 1 term and the n term is equal to a constant, and we said this constant is called a common ratio. So to show that the sequence Wn is a geometric progression, we just need to show that the ratio between the n plus 1 term and the n term is equal to a constant. Remember, the constant is called the common ratio because this constant is going to help us to express Wn in terms of n, that is finding the n term. Alright, we're being given information about Wn, about un, and about vn. Wn is equal to un plus vn. But since we need to show that Wn plus 1 divided by Wn is equal to a constant, it means we need to find Wn plus 1 because we know Wn already. Alright, so Wn plus 1 will be equal to un plus 1 plus vn plus 1, since Wn is equal to un plus vn. Now we have information about un plus 1 and we have information about vn plus 1. So Wn plus 1 will be equal to, this is un plus 1 as it was given in the equation, and vn plus 1, this is vn plus 1 as it was given in the equation. So we can distribute the 1/3 and the half all through, and we are going to get un times 1/3 is un on 3, negative 2vn times 1/3 is negative 2vn on 3, plus un times half is un on 2, plus 3vn times half is 3vn on 2. Now we bring like terms together. So we have un on 3 plus un on 2, and then negative 2vn on 3 plus 3vn on 2. That's bringing the like terms together. So un on 3 plus un on 2 gives us 5un on 6. Negative 2vn on 3 plus 3vn on 2 gives us 5vn on 6. Now since 5 on 6 is a common factor in the two terms, we can factor it out. Factoring out 5 on 6, we get 5 on 6 into un plus vn, that is Wn plus 1. But we know that that un plus vn is Wn as we had it originally. So it means our Wn plus 1 is equal to 5 on 6 Wn. We can divide both sides by Wn and we are going to get Wn plus 1 divided by Wn to be equal to 5 divided by 6. So we see that we have shown that it is a geometric progression since the ratio between Wn plus 1 and Wn is equal to a constant. So we can draw our conclusion that what? That Wn plus 1 is a geometric progression. Now the next aim of the equation is to express Wn in terms of n, that is giving the expression of its n term. Now the n term of a geometric progression is characterized by its first term and its common ratio. We have the common ratio already. It is 5 divided by 6 because it is the ratio between the n plus 1 term and the n term. But now we need the first term. So the question to ask yourself is, will the first term be W1 or will the first term be W0? Definitely the first term is going to be W0 because we have information about U0 and V0. So W0 is equal to U0 plus V0, that is negative 6 plus 1. So our W0 is equal to negative 5, and we have our common ratio as 5 divided by 6. So according to our definition of the n term, our W of n will be equal to W0 times R raised to the power n. This concept was clearly explained in part 1. Why? Because some people think maybe it's going to be W0 R raised to the power n minus 1. But no, it is W0 R raised to the power n. If it was W1, then it's going to be W1 R raised to the power n minus 1. So make sure you watch part 1 and you get the keen explanation of why it is R raised to the power n and not R raised to the power n minus 1 when we are dealing with W0. Alright, so from there, we can just express our Wn in terms of n. Our W0 is negative 5. Our common ratio is 5 on 6, and then we raise it to the power n. So we are done with Roman 1 of this question. Alright, so let us continue with the questions. So we get to Roman 2, which is asking us to find the limit as n tends to infinity of Wn. Now, since we expressed in the previous slide our Wn in terms of n, we had negative 5 times 5 on 6 raised to the power n. So the limit of Wn is simply the limit of its equivalence, which is equal to negative 5 times the limit of 5 on 6 all that raised to the power n. Because if we have a constant and we multiply that constant times a sequence and we want to find the limit of that quantity, it is the same as that constant times the limit of the sequence, because the constant does not depend on n, and we are looking for the limit as n tends to infinity. Now the next hint we are going to look at is this hint. If I have two real numbers a and b is different from 0, now the limit as n tends to infinity of a divided by b, the limit is going to give me 0 if a is less than b. We can interpret it also as, if a is less than b, it means that a divided by b will be less than 1. So a divided by b being less than 1, as n is tending to infinity, a divided by b all that raised to the power n will be tending to 0. Now if a is greater than b, it means that the numerator is greater than the denominator. Then as n tends to infinity, the limit is going to be tending to infinity as well. And if a is equal to b, then a divided by b is equal to 1. So the limit is also going to give us 1. So this is what we are going to use here. Here we have our a to be 5 and our b to be 6. So a is less than b, it means automatically the limit is going to give us 0. But 0 times negative 5 is still 0 because negative 0 does not exist. So the limit gives us 0. Alright, Roman 3 is asking us to express un plus 1 minus un in terms of w of n. Now, we have un plus 1 as 1/3 into un minus 2vn, as we had it, that was given to us initially. So un plus 1 minus u of n is equal to 1/3 into un minus 2vn, then minus u of n. Now we can bring like terms together. So we first of all send in the 1/3 into this bracket. We are going to get un on 3, then minus this un, then minus 2 on 3 times vn. Now we have that un on 3 minus un is negative 2 on 3 un, then minus 2 on 3 vn. We can factor out the negative 2/3 and we get un plus 1 minus un to be negative 2/3 into un plus vn. But what do we know about un plus vn? Un plus vn is wn. Hence, we can conclude that our un plus 1 minus un is negative 2/3 times wn, since un plus vn is wn, and hence we have expressed un plus 1 minus un in terms of wn. Alright, so we proceed with the questions. Roman 4 is asking us to show that u of n is equal to 14 minus 20 times 5 on 6 all that raised to the power n, using hence or otherwise. So hence means that you should use the previous information that you have about u of n, and then otherwise means you can use an alternative method if you cannot use that previous information. But if the question just said hence, believe me, you must use the previous information. Not using the previous information, your response is going to be marked wrong. If it said hence, show that. But since it said hence or otherwise, it means you can use an alternative method. So I'm going to use both methods so that you learn how to use both methods to prove. So I'm going to begin with the first method, which is the otherwise. So we are going to prove that u of n is equal to 14 minus 20 times 5 on 6 all that raised to the power n by mathematical induction. So this is how it goes. The first thing is to let the statement p of n be u of n equal to 14 minus 20 times 5 on 6 raised to the power n for all n greater than or equal to 0. And our main objective is to prove that the statement p of n is true. So if we prove that the statement p of n is true, it means that this is true, and we have succeeded in proving that u of n is equal to that function in terms of n. Now to carry out this mathematical induction process, we need to begin with what we call the base case, meaning we verify if the statement p of 0 is true, because if the initial statement is not true, then we cannot proceed. So for n equal to 0, we should verify if p of 0 is true. Now p of 0 being true, it means that u of 0 should be equal to 14 minus 20 times 5 on 6 all that raised to the power 0, and it should be equal to the initial value of u of 0 that they gave us. And the initial value of u of 0 that they gave us was what? Negative 6. So our u of 0 here in this scenario is 14 minus 20 times 5 on 6 raised to the power 0. 5 on 6 all that raised to the power 0 is 1, times 20 is 20. 14 minus that is negative 6. So we see that it is true for n equal to 0, since initially they gave us u of 0 as negative 6. Now let us still proceed to verify if it is true for n equal to 1. So we verify if the statement p of 1 is true. So u of 1 according to our statement here is 14 minus 20 times 5 on 6 raised to the power 1. So simplifying, we get negative 8 divided by 3. We can call it equation 1. Now according to this definition, our u of n plus 1 is equal to 1/3 into u of n minus 2v of n. So it means for n equal to 0, we can get u1. u1 is going to be 1/3 into u0 minus 2v0. But what is u0? Our u0 was negative 6 and our v0 was 1. So we get our u of 1 to be 1/3 into negative 6 minus 2 times 1. So at the end, we get our u1 to be negative 8 divided by 3. We can call it equation 2. Since these two equations are the same, equation 1 is equal to equation 2, then we can conclude that u of 1 is actually negative 8 on 3. So the statement is true for n equal to 1. Now we proceed now by using the induction hypothesis, meaning we assume that the statement p of k is true. Assuming that the statement p of k is true is the same as supposing that the statement is true for n equal to k. Now the statement p of k is actually this statement: u of k is equal to 14 minus 20 times 5 on 6 raised to the power k for all values of k greater than or equal to 0. Using this supposition, we are going to prove that it is true for n equal to k plus 1, and then we complete the induction step. Alright, so our induction step is actually using the induction hypothesis to prove that it is true for n equal to k plus 1. Now proving that it is true for n equal to k plus 1 is proving that the statement p of k plus 1 is true. And since this is the statement p of k, then this is a statement p of k plus 1. You just replace k here with k plus 1. So our main objective is to prove that u of k plus 1 is equal to this quantity. If we are able to prove this, then we can conclude that the statement is true for n equal to k plus 1. Thus p of k plus 1 is true, and then we conclude. Alright, so to prove this, we need to look for u of k plus 1. So we begin with this is what we had initially. we had our u of n plus 1 to be u of n plus 1 minus u of n to be negative 2 that wn. That's what we had previously. That's in Roman 2 of the equation. That in Roman 3, sorry, they asked us to express u of n plus 1 minus u of n in terms of wn. So we have this, that u of n plus 1 minus u of n is equal to negative 2 that wn. Alright, so it means that u of k plus 1 minus u of k will be negative 2 that w of k by just replacing n with k. So with that, we knew that in Roman, I think Roman 1 of the equation, our w of n was negative 5 times 5 on 6 all that raised to the power n. It means that our w of k, we just replace our n with k. So our u of k plus 1 minus u of k will be equal to all of this. So we have this negative 2 that here, then times our w of k. W of k is now negative 5 times 5 on 6 all that raised to the power k. We can simplify. From here, we can add u of k on both sides, and we get our u of k plus 1 to be equal to, now this one is going to give us negative 2 times negative 5, gives us 10, now divided by 3, times 5 on 6 raised to the power k. Since we are looking for u of k plus 1, we are going to add u of k on both sides of the equation. So our u of k plus 1 is equal to all of this, which is 10 on 3 times 5 on 6 all that raised to the power k, plus u of k. But from our induction hypothesis, we assume that the statement was true for n equal to k. So it means that we just replace the value of u of k with 14 minus 20 times 5 on 6 all that raised to the power k. And then we try to simplify. So 14 is a constant, so we just keep it aside. And then 5 on 6 all that raised to the power k is common between this first term and the third term. So we factor it outside. We are going to get 10 on 3 minus 20. Alright, so 10 on 3 minus 20 is just negative 50 on 3. So we get u of k plus 1 to be 14 minus 50 on 3, then times 5 on 6 raised to the power k. Alright, so from there, since we want to get this, it means we need a 20 and then we need a k plus 1 here. A k plus 1 here means that we are multiplying this raised to the power k times just 5 on 6. So we need to extract a 5 on 6 and we also need to extract a 20 so that the proof should come out. Alright, so our 14 remains there. Now 50 on 3 can be written as 5 on 3 times 10. Alright, so 5 on 3 times 10, you see that for us to have 5 on 6, so that we multiply with this 5 on 6 raised to the power k to get 5 on 6 raised to the power k plus 1, we just need to multiply. We need to have 6 in the denominator. So to have 6 in the denominator, we need to multiply 3 by 2. But multiplying 3 by 2 in the denominator, we need to multiply the numerator by 2, so that at the end we still have the same thing. So doing that, we see that the numerator here, you're going to get 5. 2 times 3 is 6, 5 on 6. Now you'll be left with this 2 here times this 10 here gives us 20. Now we can combine these 2 to give us 5 on 6 raised to the power k plus 1. So our u of k plus 1 is equal to 14 minus 20 times 5 on 6 raised to the power k plus 1. Hence, it is true for n equal to k plus 1. So the statement p of k plus 1 is true, which is what we were supposed to prove. So we conclude that since it is true for n equal to 0, here is n equal to 0 and n equal to 1, not n equal to 1 and n equal to 2. So it is true for n equal to 0 and n equal to 1, and it is true for n equal to k plus 1 as we supposed, true for n equal to k. Then it is true for all positive integral values of n, as we have proved by mathematical induction. Now let's dive straight away to the second proof, which is using the telescopic sum. For those who have not watched part 1, I explained, though I did not give more, I didn't give more details about the telescopic sum, because I said in the subsequent videos we are going to see how to apply the telescopic sum. So let's see how we can apply the telescopic sum in order to prove this. Alright, this is the information we got earlier, expressing u of n plus 1 minus u of n in terms of w of n. We have u of n plus 1 is equal to negative, u of n plus 1 minus u of n is equal to negative 2 third wn. Alright, so with that, this is actually proving it using the hence method, meaning we use the information. That's, we basically use the information that we had previously without any other knowledge to prove. So this is what we had previously. So we also express this, we just replace the value of w of n. Since this is w of n, negative 5 times 5 on 6, yeah, it's supposed to be 6, not 5, times 5 on 6. Let me correct it. Just give me a moment. Alright, so here it's supposed to be 5 divided by 6, not 5 divided by 5. Alright, so we have our u of n plus 1 minus u of n is equal to negative 2/3 times negative 5 times 5 on 6 all that raised to the power n, because negative 5 times 5 on 6 all that raised to the power n is our w of n. So our u of n plus 1 minus u of n is 10 on 3 times 5 on 6 all that raised to the power n. We even saw this when we were proving by mathematical induction. Alright, so from here, let's see what we can deduce, how the telescopic sum comes into play. Now, we can do a backward substitution. So, since u of n plus 1 minus u of n is equal to this, it means we can decrease the term by 1. So, we reduce n by 1. So, u of n minus u of n minus 1 now is going to be 10 on 3 times 5 on 6 all that raised to the power n minus 1. You see, I just decrease from n plus 1, I move to n. From n, I move to n minus 1. From n, I move to n minus 1. So, I just go backward. The same thing, I go backward again. I continue going backward till I arrive the second and the first term. So u2 minus u1 is going to give me 10 on 3 times 5 on 6 raised to the power 1. And then finally the zeroth term, u1 minus u0 will give us 10 on 3 times 5 on 6 all that raised to the power 0. Now the telescopic sum is telling us that what? If we sum all these terms, all we are going to be left with is the initial and the final terms. That's what is so good about the telescopic sum. So we are summing from the first equation right up to the sixth equation. That's what we are summing. Or we can even sum even this, but anyways, I just ended here. So summing from the first equation right up to the sixth equation, this is what is going to happen. The first term, that is in the first equation, we have u1 minus u0. In the second, we have u2 minus u1. In the third, we have we sum until we have un minus 2 minus un minus 3. We have un minus 1 minus un minus 2, and then we have un minus un minus 1. So this is what we are doing. Now I've highlighted some things so that you see how the telescopic sum actually works. Like we said in part 1, we said that the telescopic sum is simply a sum where it's a telescopic sum. The telescopic series is a telescopic sum where subsequent terms cancel each other, leaving just the initial and the final terms. Let's see how it goes here. This term in red, u1, you see that u1 in the first term is positive, but in the second term it is negative. So since we are adding, it cancels. Now u0 is negative, so you see u0 remains intact because you cannot find u0 in any other term. Now if you go to u2, you see it is in yellow. It cancels with the u2 in the next term. So you see the terms are cancelling out. Now let's talk about the n terms this time around. Un minus 2 is going to cancel out with un minus 2 here. You see this un minus 2 here strikes off with this negative because we are adding. Now this un minus 1 here strikes off with this. Let me try to do the striking off so that you clearly see. So when we add, we see that this term here cancels with this term. Now this term here cancels with this term, and so on. You see this term here cancels with this term. Now this u2 here, maybe you cancel with a certain term up here if we included those terms. Now this u of 3 here is going to cancel maybe with a certain u of n minus 3. So finally you see that you're just going to be left with what? U of n and negative u of 0. That's what we are going to be left with. So we see that at the end we are going to be left with just this. Alright, so with that, we summing that this what we are doing. The first term, which is this, plus the second term, which is this, plus the third term, right up to the n minus 2 term, and then the n minus 1 term. That's what we get. Alright, so we clearly see that what it is a geometric sequence. It is a geometric sum. because you have the powers of 5 on 6 is increasing as you are adding and going. You see the 10 on 3 is constant. Our 10 on 3 is constant, so we can simply identify this as a GP. The n term of the GP is what? 10 on 3 times 5 on 6 raised to the power n, or n minus 1. This is the n term, the final term. So this is the n term of the GP. So when it is 0, when it is 1, and so on and so forth. So like I also explained in part 1, I said that if we are summing from 0, that is from 0 right up to n, we have n plus 1 terms. Because if you sum from 1 to n, we have n terms. So adding the 0 term, it means you have added 1 term, so it's n plus 1. But in this case, we are summing from 0 and we are ending where? We are ending at n minus 1. So it means we have n terms, because it is equivalent to summing from 1 to n. So summing from 0 to n minus 1, we have n terms. So this is going to give the formula for this GP is going to be the first term a times 1 minus r to the n, all divided by 1 minus r, because we have n terms. Alright, so it means our un minus u0, because all of this sum is equal to un minus u0. It will give us the sum from k equal to 0 right up to n minus 1 of 10 on 3 times 5 on 6 all that raised to the power k, because that is the n term. So with that, we are going to we just replace the formula. This is what we are summing. We just have un minus u0 to be, the first term is 10 on 3, that is for k equal to 0. Because k equal to 0, all of this is going to give us 1. Then times the 10 on 3, we have 10 on 3. 10 on 3 into 1 minus 5 on 6 to the power n, because our common ratio is 5 on 6. All divided by 1 minus 5 on 6. 5 on 6 is the common ratio. Now 1 minus 5 on 6 is 1 on 6. We just do some simplifications, and then you see the 6 goes up, meets with 10, you get 60. We divide by 3, we get 20. So we have u of n minus u of 0 to be 20 into 1 minus 5 on 6, all that raised to the power n. Alright, so we can distribute the 20. We get un minus u0 to be 20 minus 20 times 5 on 6, all that raised to the power n. Since you are looking for un, our un, you need to add u0 on both sides. But originally we knew that what our u0 is negative 6. It means that our u of n will be 20 minus 20 times 5 on 6 raised to the power n plus negative 6, which is the same as minus negative 6. 20 minus 6 is 14. So our proof comes out automatically. Our u of n is equal to 14 minus 20 times 5 on 6, all that raised to the power n. Alright, so Roman 5 is asking us to study the sense of variation, that is the monotony of the sequence un and the sequence vn. So studying the variation is to determine if it is increasing or it is decreasing. Watch part 1 of the video, you're going to understand more how to determine if a sequence is increasing or the sequence is decreasing. We are going to do it here still. So we need to determine, we know that u of n plus 1 minus u of n. Basically, right, to determine if a sequence is increasing, we just need to do the difference between, we need to know the sign of the difference between the n plus 1 term and the n term. If the n plus 1 term minus the n term is less than 0, then it is monotonic decreasing. If it is greater than 0, it is monotonic increasing. So in this case, we already have the difference between the n plus 1 term and the n term of the sequence un. It is 10 on 3 times 5 on 6 all that raised to the power n. Basically, it was negative 2/3 wn, but when you simplify and input in the value, the n term of wn, you get this. So we just need to determine if this right hand side is greater than 0 or is less than 0. But clearly it is greater than 0 because n is a natural number. 5 on 6 is positive. So raising a positive number to a positive number is positive. Multiplying by a positive number is positive. So we clearly see that what our un plus 1 minus un is positive. In conclusion, un is monotonic increasing. What about vn? Our vn plus 1 minus vn. This is vn plus 1. It was given to us initially, then minus vn. Now we can bring like terms together. So we first of all multiply all through by half. We get this. 3 on 2 vn minus vn is just 1 on 2 vn. So we have Vn plus 1 minus Vn to be half Un plus half Vn, which is half into Un plus Vn. But what is Un plus Vn? It is Wn. These are the various informations. Un plus Vn is Wn. It means that our Un plus 1 minus our Vn plus 1 minus Vn is equal to half of Wn, since Un plus Vn is Wn. Alright, what do we know about Wn? Our Wn is negative 5 times 5 on 6 other raised to the power n. So we just need to determine the sign. Since this quantity is positive, if you multiply it with negative 5, it is going to be negative, because multiplying both sides by negative 5, the inequality sign changes. Alright, so with that, we see that our sequence Wn is negative. Clearly it is negative because just this part here is positive, but the negative 5 multiplying it makes it to be always negative. So since the sequence Wn is negative, we can multiply both sides by half so that we get Vn plus 1 minus Vn. So multiplying both sides by half, we still get it to be negative because half is positive, so the inequality sign is going to remain less than. So we can conclude that the sequence Vn is monotonic decreasing, since Vn plus 1 minus Vn, which is half Wn, is less than 0. Alright, so next we are going to find the limit of Un, and then we deduce the limit of Vn. Now the limit of Un is simply finding the limit of this guy here, because this is our Un, we proved it earlier. So the limit of Un is the limit of all of this. The properties of limit we can separate. So the limit of 14 is 14 because it's the limit of a constant times the limit of all of this. The limit of 20 times this function in terms of n is 20 times the limit of that function in terms of n. Alright, since we do the very recall, we recall this earlier. This limit is going to give us 0 because 5 is less than 6. So it means this limit is going to give us 14 minus 0. So the limit of our sequence Un is 14. Now we have to deduce the limit of the sequence Vn. We have to deduce it. So we are not finding the limit of the sequence Vn, we have to deduce. So if you watch part 1, we talked about something. We said that there are some sequences that we call them adjacent sequences. And what are they? These are just two sequences that are defined recursively, meaning one is defined in function of the other, such that one of them is increasing and the other one is decreasing. And we said that these two sequences converge to the same limit. So in Roman 5 of the equation, we proved that we saw that our Un was increasing, and then we also saw that Vn was decreasing. So with that, we see that what? They are adjacent sequences because originally they were defined in function of themselves. Un was defined in function of Vn, and Vn was defined in function of Un. So they are adjacent since one is increasing and the other is decreasing, and they were defined recursively. So automatically we can conclude that the limit of Vn is also 14, since Un and Vn are adjacent sequences. That is why they use the term deduce. We are not finding. If you go ahead finding, you're out of the track. Alright, the last part is asking us to evaluate the sum from n equal to 0 to infinity of Un minus 14. So Un, we just replace anything you see in red is Un. As you can see, Un is 14 minus that. So 14 minus 14 is going to give us 0. So we just get the sum from n equal to 0 to infinity of negative 20 times this. We can bring out the negative 20, and then we see that this is what? A GP. You have to find the sum to infinity of a GP. The first term is when n is 0, which is 1, and the common ratio is 5 on 6. Alright, so with that we just simplify and we get our Un, that is the sum from n equal to, so this is the sum to infinity, U0 over 1 minus R. That's the formula. That is for the absolute value of R less than 1. That's for the convergence. So finally we get that sum to be negative 1 divided by 20.